Great, so we're just going to jump in. So we're going to start the session in Antarctica, like you just said. The floating portions of ice that fringe the perimeter of the ice sheet, known as ice shelves, they control the amount of ice that makes it from the interior of the ice sheet into the ocean. So understanding the controls on ice shelf stability are critical in order to predict the future evolution of the ice sheet, as well as future sea level rise. This is a velocity map of Antarctica, and I like it because it shows flow lines as well, and you can really visualize how these ice shelves are draining the inside and interior of the ice sheet and funneling them into the ocean. Most of the time I'm going to focus on the Ross Ice Shelf, which is the largest ice shelf in Antarctica. One of the most important locations for the Ross Ice Shelf is its western lateral margin, known as the McMurdo Shear Zone. This McMurdo Shear Zone is providing resistance to the flow of the Ross Ice Shelf, and so imposes a critical control on the stability. One note I should make is that north is going to be pointing down in this orientation, just to orient yourself. All right, so what causes the McMurdo Shear Zone is that ice on the Ross Ice Shelf is moving quite fast, but as it comes in contact with the ice flowing on the McMurdo Ice Shelf side, which is buffered behind this rock outcrop here called Minna Bluff, this strong velocity gradient creates a shear zone that's is 5 to 10 kilometers across and heavily crevassed. And we're interested in the shear zone because a change in resistance supplied by this region will have implications on overall Ross Ice Shelf stress balance and stability. And in particular, it'll have drastic effects on the distribution of backstress at the grounding line, or the point where glaciers feed into this ice shelf and become ungrounded. One way to visualize ice shelves and understand them is they're kind of like a cork in a bottle. So if you remove that cork, the glaciers behind them are able to flow freely without any resistance. One key example of this, a drastic example of this, was the disintegration of the Larsen B ice shelf back in 2002, where in a matter of months, the entire ice shelf disintegrated. And while the ice of the ice shelf does not directly contribute to sea level rise because it's already displacing the ocean, the glaciers that feed into the Larsen B, they experience a 2 to 3-fold increase in their velocities. And that the velocity pattern has still stayed elevated compared to pre-collapse conditions. So again, ice shelves are key in providing resistance to the flow of the glaciers that feed them. This region is also of interest for logistical purposes, in that the United States Antarctic Program has to cross the McMurdo Shear Zone on a yearly basis in order to get supplies from the McMurdo base out on the edge all the way to the South Pole in the interior. So what they did in 2002 is they created a route called the South Pole Traverse. The gray line shows the 2002 location. And the McMurdo Shear Zone region, even though it's heavily crevassed, all the crevasses are beneath snow bridges. So what they do to mitigate the hazards of crevasses is they open up the crevasses with explosions every year, and then they fill them in with snow. So it takes a lot of effort to do so. Another key point I want to make is that because the ice shelf moves, the route itself is infected, and it's infected into its current location 2019. And they've noticed that on a yearly basis, more and more crevasses kind of mitigate. So through time, it's been infecting into a more hazardous region. So they're currently hoping to move the route to a new location, and our field observations from this survey will help determine that location. So just a brief overview of the method that I'm going to present today. We're combining crevasse observations from ground penetrating radar, GPR surveys, with kinematic outputs derived from remotely sensed ice surface velocities. And we're doing this in order to develop a statistical method to investigate the kinematic drivers of crevasse initiation, and then to estimate crevasse initiation threshold values. Is there a particular kinematic output that we can use to predict where crevasses will be and how they will evolve in the future, simply for remote sensing data sets? And then we're going to apply this method, and I'm going to illustrate this today in order to determine an optimized location for the South Pole Traverse and to study its future viability. So for our GPR surveys, we completed an expedition in 2017, and we covered a 5.7 by 15 kilometer grid. And that can be seen in this white box. And this survey was designed to investigate the spatial distribution of crevassing upstream of the South Pole Traverse crossing, so above the 2002 location. And we collected, at least for this work, we collected 21 different transects within this box. And the way we did this is we deployed two four-wheel drive battery-powered rovers. These were designed by the Thayer School of Engineering specifically to tow our GPR units back and forth across the shear zone in a safe manner. And using this method, we were able to collect up to 100 kilometers of high-resolution ground-penetrating radar data. The next thing we did was look at the kinematics in the region. To do so, we derived different outputs from remotely sensed velocity fields. A couple of the outputs we looked at are dilatation, or the local expansion, vorticity, as well as shear strain rate. And that's mainly what I'm going to focus on today because it proves to be the best in terms of predicting where crevasses would be located, at least in this particular region. So again, we derive the shear strain rate looking at the gradients in velocity. We plot the crevasse locations that we found across our 21 different transects on top of our map, and we extract the shear strain rate for each of those crevasses. We can then look at the relative frequency to the number of crevasses versus the shear strain rate. And spatially, you can see in regions of lower shear strain rate, there are a lower number of crevasses, and this came through in our data analysis. Another key point is that we found a threshold beneath which we didn't find any crevassing. And we found this crevasse initiation threshold at a shear strain rate of 0.0114, and we can use that in order to move forward. So real quickly, we'll look at a couple spatial patterns. Again, visually or qualitatively, if we're looking for an ideal place to place the new route, we would look for a minimum in shear strain rate, perhaps in this area, or near where the route was initialized in 2002. And across the different transects, we delineated 420 crevasses, and 323 of those crevasses, based on their size, would require mitigation. And those earlier places that I just pointed out actually match with the minimum number of crevasses. So the next thing we wanted to do was look at these two different places, choose an ideal route in those two locations, but not just look at them in one point in time, but to predict the overall evolution and the kinematic field they're going to flow through. So what we did was we initialized this top route, and we advected it 20 years into the future based on the current velocity field. We then looked at the shear strain rate of each of those yearly locations, and anything but in this off-white color is beneath that crevasse threshold. Let's compare that to the lower route, which starts again a bit lower. Even though this route was initialized at an overall lower shear strain rate, we can quickly see that it advects through a wider region of the shear zone. And the next thing we can look at is the percent of the route that's above that threshold. For Route 1, about 50% of the route would be subject to crevassing over the next 15 years, whereas that second route steadily increases to almost most of it being subject to crevassing. We can take this one step further and predict the number of crevassing we would expect over the next 20 years. And again, you see an increase in the lower route, whereas the top route seems to be stable. This actually mimics some of the observations that the South Pole Traverse found when they were mitigating crevasses over the last 20 years. So again, starting at 2002 and affecting through 2018. And while the number of crevasses doesn't match, they have a more robust way of delineating crevasses. The trend holds. So just a couple of takeaways as I'm running out of time. I hope I've shown that kinematics can be leveraged as a powerful tool, especially in optimizing safety in these heavily crevasse regions. For our particular area of interest, shear strain rate occurred at a minimum, crevassing occurred at a minimum strain rate of 0.0114. And while this particular initiation or crevasse initiation threshold for our field site can't be directly transferable to other field sites, our method can be mimicked and used to monitor dynamic changes in these regions. And with that, I'll answer your questions. Great, thank you.
Next we have Aaron Chesler, and he will be talking about Holocene changes in the Westerlies from ice core record from Antarctica. Yeah. All right.
Thanks, Scott. Okay, thank you. I'm excited to share with you today why I believe the South Pole ice core dust particle record might provide evidence for a cooler early Holocene. And the early Holocene is a really important time period within Earth's recent climatic history. It is the last time period when Earth's temperatures were similar to those of today. And we can see that through temperature stacks that have been taken from proxies collected all over the globe. And so over here on the left side of the screen is the Marcotte et al. 2013 temperature stack. With the early Holocene over here, we're reaching the Holocene thermal maximum around 8,000 years ago. At 6,000 years ago, there's a general decrease in global temperatures, and followed by the recent uptick due to anthropogenic climate change. However, when we start picking apart these proxies by individual regions, we can start to notice a different trend in that data. Over here, plotted by Dawson Alley 2008, are melt frequency layers from ice cores in Greenland and Antarctica. And melt layer frequency is a powerful proxy record. It's a physical proxy record that is just recording melt layers in the ice core during the formation in the firn process. So what it simply states is the higher the frequency of the melt layer, the warmer the time period, and the lower the frequency, the cooler the time period. So if we look at GISP2, which is in the gray, that's from Greenland, you can see that the profile in the melt frequency layer record mimics the Marcotte et al. Temperature stack, where we have a very warm early Holocene followed by a decrease in the Neoglacial. But when we look at the Antarctic record from the Cycle Dome record, we're showing an opposite trend, where during the early Holocene, there's almost no melt layers. The melt layer frequency decreases to about 0. And so it's important to understand what's regionally going on in Antarctica because it's showing a very opposing trend towards the North Atlantic. Now, one proxy record that we can use to study the Southern Hemisphere is through the Southern Hemisphere westerly winds. This is NCAR analysis data derived from the Climate Reanalyzer, and it's just showing wind speed in meters per second at 850 millibars in the atmosphere. And you can see on here that the Southern Hemisphere westerly winds, which is the wind current down here where all the colors are, is the strongest wind current on the planet. It's a very powerful current that dictates Southern Hemisphere climate. And so Kaufman et al. Used the Southern Hemisphere westerly winds during the drilling of the Waste Divide project and measured dust particles in the ice core. And dust particles are a very useful proxy for understanding how the Southern Hemisphere westerly winds are fluctuating. So from their research, they derived this hypothesis, or this idea, that during warmer periods, so over here on A, when the westerly winds are latitudinally contracting southwards, there's a shift in the particle sizes towards increasing or more coarser particles. During climatically cooler periods, the winds have latitudinally fluctuated north, you're increasing the relative amount of finer particles in each layer. And when the wind, so again, during warmer periods, the winds are contracting, you're increasing your upwelling derived from wind stresses on the ocean, you're increasing the amount of coarser particles, and then during climatically cooler periods, you're increasing the amount of finer particles. And so that was their hypothesis, is that the dust particles or the sizes of the dust particles relates to how the westerly winds are fluctuating. However, the waste divide record only goes back 2,400 years. And so we can use the South Pole ice core, which is annually resolved throughout the Holocene, to understand what was going on during the early Holocene in Antarctica. And so we can extend that record. For our methodologies, we use the same methods as Kaufman et al. We use continuous flow analysis, and specifically an Abacus laser particle counter, to measure southern hemisphere westerly wind variability. And from our initial results show this. So this is the particle size distribution throughout the entire Holocene. We sampled at 2 intervals. There's 10-year, which is background data, and then 100-year, which is in black. And so if we zoom in on so we need to calibrate this record to understand fully what's going on and what the South Pole is representing, or what the South Pole dust is representing. So if we zoom in to the 20th century, over here is 1880, over here is the year 2000, we see generally increasing towards coarser particles. But before we can make any strong conclusions about what is happening in the 20th century, we need to know where the dust is coming from and what it's affecting regionally. So using the climate reanalyzer, and this is just using meridional wind speed directions. So blue up here, blue is depicting a southward flow, so going from the north to the south, and then the red is depicting a northerly flowing wind, so from the south moving north. And so to get wind and dust to the South Pole, it's moving in through 2 locations, into the Weddell, which is the arrow right here, and then also through Western Antarctica down here. And now if we back that out using modeling and strontium neodymium and other isotopic geochemical data, we can back out that the dust for the South Pole is predominantly coming from South America. So that's great. So now that we know where the dust is coming from, we can start making some correlating relationships. So that's exactly what we do. We start taking that 20th century record, or at least from 1948 up to 1992, which is the start of our record, and we start correlating that back to climatic proxies or conditions. So over here, I've plotted mean sea level pressure through the austral summer, and we're seeing a very strong coherence throughout, or spatially coherent record throughout Antarctica. If we correlate the same record back through the austral winter, we're seeing a very different relationship. We're seeing a breakdown of that coherence, or that spatial coherence throughout the region, but still generally a fairly positive correlation throughout there. If we start looking at atmospheric zonal wind speed, we're seeing a very different correlation. We're seeing a negative correlation throughout surrounding Antarctica, through the austral summer, and then during the austral winter. We are also seeing a fairly anti-correlation or negative correlation throughout. However, we are picking up some small positive correlations in New Zealand, and then just off the coast of Western Antarctica. And I'd like to point, and we're going to zoom in on the Western Antarctica here, and we're going to compare these, the 20th century particle size distribution data back to oceanographic records. So in the very beginning, I mentioned that with contractions of the southern hemisphere westerly winds, there's also increased ocean upwelling. And ocean upwelling contains different signatures of carbon in it based on the amount of CO2 that's in it. So this data is from Hillenbrand et al. Down here. They studied recent upwelling events just off of Pine Island Bay, off of Western Antarctica. And what they noticed that during about the 1940s to about the 1970s, there was a shift in the delta 13C values towards lighter values. And what they interpreted that as is increased circumpolar deep water advection. So during this time period, there's increased movement of this deep ocean water mass that is rich in CO2 up to the surface. And at the same time that Hillenbrand et al. Found increased circumpolar deep water advection, there's also a shift in the southern hemisphere westerly winds towards coarser valleys. And so at the same time that the winds are increasing in coarseness, we're also seeing an increase in circumpolar deep water advection of rich CO2 up to the atmosphere. And so with that, I think the SPICEcore, South Pole Ice Core dust particles are reflecting these broad scale southern hemisphere dynamics. And so when we back that out, looking at the entire Holocene with coarser particles reflecting increased advection of the CO2 rich deep water, it might suggest that the early Holocene with a general background of finer particles may be cooler with decreased advection and more northerly latitudinally displaced wind field. And with that, I also just wanted to note that I'm still working on that middle section there. I'm still analyzing this record as well. So with that, I'd like to thank everyone and my committee members as well.
Okay, I'd like to welcome up Will Kochtitzky. He's going to be looking at glacial lake fluctuations and association hazards all the way up to Canada. So we'll take a
Thanks, Scott. Yeah, so I'd like to talk today a bit about some of the work I've been doing in trying to better understand some of the hazards associated with Donjek Glacier and river in the Yukon. So Donjek Glacier is here in southwest Yukon in Canada. It's right along the border with Alaska. It's situated on the north side of the St. Elias Range, so it's a relatively dry and cold climate here in the southwest Yukon. Donjek Glacier is really interesting, in part because in the past it has caused this big lake to form, which is in the literature has been called Paleo Lake Donjek. So here's Donjek Glacier. In the past, and as recently as the early 1800s, the glacier advanced all the way across the valley that you can see here and blocked the river, Donjek River, that comes from upstream from Kewaunee Glacier. So this Paleo Lake Donjek formed and was quite large. When you do the calculations out, it comes out to about 87 meters of water over the 660-acre Union campus. This is about 3.5 times the volume of Pushaw Lake down the road. So to give you a sense, this is, was quite a big lake that was forming, and there's geomorphic evidence to suggest it formed at least in the early 1800s, and likely before that as well. This is important because there's infrastructure and people downstream of this glacier and river. So here's Donjek Glacier. Donjek River flows here, and about 50 kilometers or so from the terminus of Donjek Glacier is the Alaska Highway. The Alaska Highway crosses Donjek River here, and of course the Alaska Highway is a really vital connection between not only the lower 48 states and Alaska, but also Western Canada. So this is an important bridge for the movement of people and the economy. This area is also hunting grounds and fishing grounds for the Kewaunee First Nation. So they're particularly concerned about this valley and what goes on here, as well as Parks Canada. This is in the national park, Kewaunee National Park. And so Parks Canada is concerned about researchers or recreationalists or anyone who might also be in this valley if there was a flood here again. So part of the reason these floods can occur, there's concern here, is that this glacier goes forward and back. So it retreats and then it advances on a cyclical basis. It's a surge type glacier, which is a bit unique in the world, but not uncommon in this part of the world. Here's an example of the 2013 surge event. So in 2012, the glacier terminus was retreated, it was further back. Over the course of 2 years, the glacier rapidly advanced up to a couple kilometers in places. You can see this is the Donjek River flows right in here. And so the glacier advanced and approached upon the river here. In the recent past, Donjek has undergone multiple of these surge events quite frequently, every 12 years about, since at least the 1930s and likely before that. You can see here in The black bars indicate times that we're really certain the glacier surged during this time. The black bars show that the active phase of the surge event was occurring that entire time. Further back in time, we're less certain because we have old air photos and we can't pin it down quite as well. But you can see the regular surging is really remarkable. It really does go about every 12 years. This has been happening since at least the 1930s, likely longer. Over the same time, you can see that the surge extent has become less and less. The glaciers are retreating up the valley. So here is where the glacier sat in the late 1800s. And the maximum surge extent, or the position the glacier was after this advance, this period of advance, has gone back up the valley. So here in 2014, after its most recent surge event, it's much further back than we've seen in the record. So this is important to know because Donjek River is flowing here. So the Donjek Glacier is actually moving further and further away from Donjek River. Yeah, this is implying that it's quite unlikely we're going to dam Donjek River again completely. So here's one of the first photos we have, or the first photo we have of a lake on Donjek Glacier and Donjek River. This lake formed and was captured in the mid-1950s. More recently, this is from last summer. You see this lake formed, and this is quite a significant lake now, but nowhere near the size of Paleo Lake Donjek, which we showed earlier, which would form back here. So you can see now this the current edge of Donjek Glacier is quite far from the other valley wall. So I think it's quite unlikely that you might form this Paleo Lake Donjek again, although we don't know how the glacier will react to the future, but there's quite a big gap here now between Lake Donjek Glacier and the valley wall. So it seems really improbable that we're going to form Paleo Lake Donjek again, but we seem to be forming these relatively smaller lakes more frequently now, which I'll spend the rest of my time here showing you pictures of. So in the late 1980s, Donjek Glacier underwent a surge event. So in 1988, it surged. You see there was this little lake here present at the beginning of the surge event in 1988. By 1989, the lake was even smaller. And by 1990, the lake was gone. So it looked like this surge event almost squeezed the lake out. It just displaced the water and advanced across the valley. And the lakes were basically displaced. I don't think, from the images I looked at, I don't think there was a flood that came from this event. The 1990s has a bit of a different story. So in 1997, we can see there was this lake here that was present. In October of that same year, the lake was gone. It's difficult to say with the satellite imagery we have when exactly that drained or how long it took to drain, but it appears that it drained quite rapidly. And you can see in 1999, there's this the river had cut all the way through the edge of the glacier here, forming this ice canyon, which I imagine would be quite spectacular to raft down. You kind of with the glacier on both sides, and the river is kind of cut through it. So I think what's happened here is the river has drained underneath and undercut the glacier, and the roof has basically fallen in on it. So you have this river now cutting through the glacier. More recently, Donjek Glacier surged in 2013, and it created these lakes here. Those lakes have grown, and in 2017, this was the lake on August 15th, and it was gone on August 16th. So this is pretty convincing evidence that the lake can drain quite rapidly. Here we have a really rapid lake drainage and quite substantial. Just the different colors here are just different satellites. This is Landsat on the left and Sentinel on the right in a false color composite image. So the important thing here is to focus on the lakes. So here's some air photos of this event in May 2017. You can see the lake here. The lakes were full. By August of that year, the lakes were gone. We know that happened right around August 15th or 16th from our satellite images. You see here that the river is starting to eat under the ice in that same place. So I wonder if this is kind of like what happened in 1999, where we're going to form this really spectacular ice canyon again as we continue to undercut the glacier, and that roof might eventually fall in. This past summer, we also had another lake drainage event. So the lake drained in 2017, and then in winter 2017, 2018, the lake reformed. July 2018, we see the lake even larger now, and by the end of August, it was gone again. So this is again quite dramatic drainage event. Actually this was taken from Sunday, from a Planet Labs satellite. This is what the lake looked like on Sunday, and I imagine it looks much the same right now. The lake is quite large, and it appears poised and ready to go again, potentially this summer. You also see how it's starting to undercut here. You can see the roof of the glacier starting to cave in, so I do think we're going to see this canyon start to form in the next few years. You'll have a full-blown ice canyon here. That's going to be where Donjek River is going to be routed through. So the current Lake Donjek is not nearly as substantial a threat as Paleo Lake Donjek was. This is only maybe a quarter to half the volume of Pushaw Lake here in Orono. So it's not nearly as big a concern as Paleo Lake Donjek. But this is the largest lake we've seen here forming from the air photo and the satellite archive. The lakes appear to be getting bigger through time, not smaller, even though the glacier is retreating. We also don't know how the future is going to evolve in this. This area has been really poorly mapped, and we don't know if the lakes will continue to grow as the glacier continues to retreat, or if the lakes will stop forming altogether as the glacier retreats. So this summer, we're hoping to continue some field work we've been doing and trying to better map this area. We really need to map what the lake bed looks like once the lake has drained, if it does drain again in August. Hopefully we'll be able to get some elevation models to then get a volume for the next time it fills. We also need some better data to better understand how quickly these lakes drain. Right now, the best we can do is an image a day from the sky if there are, from satellites, if there are no clouds. Getting down to this kind of time-lapse photography and maybe the 10-minute scale would be really quite wonderful. And I'd like to thank everyone, especially the NSF and Dan and Betty Churchill, for helping fund the work. They got one of those air photos. Thank you. Yes?
I know basically nothing about glaciers at all. But I'm curious, I know you said that probably that paleo lake will form again. But if it were possible that it would form again, how quickly would that get blocked off, and how quickly would water rates start backing up? Is that something that's going to happen in a day, a week, a month?
Yeah, that's a good question. It would depend on the discharge coming from Huani Glacier, which is upstream there. So yeah, it would, if it were to close again, I think it would close quite slowly because the glacier would need to come all the way across the valley. So we would definitely be able to monitor that as it advanced. But as for how quickly that lake would fill, I would guess in a matter of weeks. This is a lot of water that can come down through here, especially in the springtime. This time of year, when the snow's melting, there's a ton of water. So yeah, it could fill quite quickly, but we would have a fair bit of warning, fortunately for this type of system. And we've been in touch directly with Parks Canada. They're really quite concerned about this. And they would be the first to know that this area is undergoing those dramatic changes.
How do we get in there?
There is, let me see if I have it here. This is Burwash Landing. So we can take helicopters from there, or Huani Lake Research Station is just across the lake. There's an airstrip in Silver City.
We get it by helicopter.
Or fixed wing.
Where do you land?
Well, you can actually land on a lake up here, or if you have a float plane, or or higher up, or we just take air photos with the fixed wing.
And once you land, how do you get around the run?
Higher up we can ski, but if you land down here, then you have to hike. Yeah, it's really tough work. You can also hike. There's a really amazing trail that comes from the Alaska Highway up over the Donjek range here, and then you can hike in. But you've done this before, right? So
We use horses.
horses would be great. I'd love to go on my horseback.
When you experience the first time when you try to cross the river in a horse and roll. I can show you some pictures.
That'd be great. I'd really love that. Thank you.
Okay, I'd like to welcome Edna Pedraza Garzón, and she'll be talking about understanding key diatoms and outliers.
Hello. So today I'm going to To talk about the second part of my study in Aulacoseira, first of all, I want to give thanks to the Tertiary Exploration Fund and to the Saros Lab because they helped me to work in this. So the first thing to say is that the water stability in lakes is product of the interaction between climatic and physical aspects. The lake acidification is product of the absorbance by water of solar energy and the capacity of transport that heat through the water column. However, in general terms, that thermal profile is modified by the effect of seasonal changes in atmospheric temperature and also by the interaction of winds and precipitation because they act as disrupting factors for the stability. So when the interaction of those physical factors and the interaction of those factors with light and the detonation of light and the temperature and the trophic status in lakes determine the composition of algae community and the changes that occurs depending on the conditions of the lake. So basically, the species are present in those lakes depending on functional traits that they have and the capacity to withstand the changes in the water column stability or to take advantages of the stratification or the mixing in the lakes. The study of long-term variation in lakes by the use of sediment cores allowed to detect in which period the lake experienced changes in composition. And in terms of the changes in stability, particular attention has been focused on the cyclotherapy species in Aulacoseira. Important advances has been done in cyclotherapy species, basically by the work of Saros. And there are suspicions about the importance of Aulacoseira. Starting 2015, studying sediments from alpine lakes in Rocky Mountains found that prior the period 3.1 K and after 15,000 years, those lakes had a prolonged stratification period based on the changes in abundance of some cyclotherapy species. So they suggest that between those years or between that period, the lakes experienced instability during the Holocene, and that suspicion is also fortified by studies in northern Andean lakes, in lakes that have constant mixing. In the sediment record, they found frequent, constant, and abundantly presence of Aulacoseira species, like Alpagina and distance. However, there are still some doubts about the accuracy of these predictions or reconstructions because there are some gaps in the ecology of Alpagina and Aulacoseira species. So it's important to understand or to have a clear idea about how Aulacoseira species respond because based on the changes in cyclotherapy species and Aulacoseira, it's possible to associate changes in the climate, like the study from starting 2015. He studied the changes in the Eolithian law and the changes in the mixing. So he identified periods of a strong mixing with periods of strong changes in the Eolithian law. So if we have a clear idea about how Aulacoseira respond to mix in, but also other factors we can understand if turbulence is the only or the main factor that determines the presence of Aulacoseira in the lakes. And we can also determine if Aulacoseira presence in lake is also affected by other factors like temperature or light. So to answer these questions, in my fieldwork in Montana, I sampled 3 lakes, 2 alpine lakes and 1 subalpine lake. Basically, the alpine lakes are Beauty and Beartooth, and the subalpine lake is Kersey. And to answer those questions, I did vertical profiles in those lakes and also microcosm experiments testing the effect of nutrients. So I add nitrogen, phosphorus, and nitrogen and phosphorus in microcosms, and I also test the effect of changing the intensity of light. So here you see what I used for simulating conditions of total light access, 60% of light access, and 25% of light access. What I found was that for Kersey, the dominant species is Aulacoseira distans. I found that the main or the highest densities are located in the surface of the lake. It's important to say that this lake has been already stratified by the time that I sampled it. For Beauty, the distribution of Aulacoseira alpigena was found between the equilibrium and in the middle of the lake and in the bottom of the lake. And for Beartooth, the same species, Aulacoseira alpigena, was found along the metaline. So basically what we found is that there are certain preferences for the location of those species, and from the experiments that were only done using water from Kersey and from Beauty, the most significant changes are between the addition of nitrogen and phosphorus versus the sample that doesn't have any nutrient addition. And the most significant effect was found for the location. So basically, the location in the water column is important to stimulate the growth of Aulacoseira. And in terms of light access, basically the species, these samples were incubated on the same water depth, so they had the same temperature. So in this case, we can see that light is a determinant factor that stimulates the growth of Aulacoseira alpigena. For Beauty, in this lake, we have for Kersey is distance, and for Beartooth is alpagena. In this case, again, the location is the dominant driver of the growth of Aulacoseira. And in this case, even though the algae were exposed to the same temperature conditions, basically the absence of light stimulates the growth of Aulacoseira. So in summary, what we can see here is that light is a determinant factor for Aulacoseira alpigena, and for Aulacoseira distance is temperature and light. So we can also test the effects of temperature, and we can say that nutrients are not a determinant factor in the occurrence. Thank you.
Okay, next we'll welcome Charles Rodda. He'll be talking about an ice core from Central Asia.
Well, since I updated you guys last year on our work on this ice core, we have completed continuous melting of the entire 37 meters of the ice core and targeted ultra high resolution laser ablation sampling of 14 targeted sections of that core. I'm going to give a number of really exciting stories that started to emerge. There we go. Conclusions up front. In the next 10 minutes, I'm going to try to convince you that I have a 2,000-year ice core chemical record, that I've got evidence going back that full 2,000 years of anthropogenic heavy metal pollution in Central Asia. It includes such exciting features as bubonic plague in Europe. Also that I can show you individual years back as far as 1,600 years ago in Central Asia, and that we have something to say about differences in annual atmospheric circulation patterns in the Little Ice Age, medieval warm period, even pre-medieval warm period in this region. So I'll be moving pretty quickly, trying to avoid that clam up sign. This is our study region. Of course, the red map corresponds to the red square on the globe there. We're interested in the 6 Central Asian countries. Our regions extend from Kazakhstan in the north to Afghanistan in the south, from the Caspian Sea Basin in the west over to roughly the Tibetan Plateau in the east. Circulation in this area is dominated by the westerlies. Most of the air and moisture that comes into this region comes from Central and Northern Europe over the northern part of the Caspian Sea. It ends up at our ice core site marked there with that pink dot. Of course, this region is incredibly arid. Almost all of the moisture that ends up here ends up right up in the highlands here in Tajikistan and Kyrgyzstan. They function really as a water tower for the rest of the region that receives essentially no moisture whatsoever. Significantly, that shows up as during a critical cold, wet season. Right? This is the seasonality. This is the reason why we're really interested in what happens in individual years and individual seasons in Central Asia, because there's this critical end of the winter where it's still cold, March, April, May, where it's cold enough in the highlands, above 5,000 meters in Kyrgyzstan and Tajikistan, for the moisture that shows up to fall as snow, where it can remain until the summer, where it then melts, flows down through these major river valleys, the Sirdarya and the Amudarya, towards the Aral Sea Basin, and is available for, of course, for natural biotic communities, but also for hydroelectric power generation and for, importantly, for irrigation to the humans that live there. There's about 75 million people live on that map that I showed you, and this is there's no moisture really that falls in Uzbekistan and Turkmenistan, where they grow the grains that feed them. So that's why we're interested in this critical overlap of cold and wet in March, April, May, because very soon after that it gets hot and dry, and that's when they need the water for growing. Some alarming trends in the 20th century in the highland, the high countries. Purple and red here is Kyrgyzstan and Tajikistan, where that water collects, when the water fills up that water tower, it's getting drier there, and also you see it's warming. So that critical seasonality that we see is threatened. We look back over the last 2,000 years, we have periods that are warmer, wetter, and less windy than it is now. That's the medieval warm period outlined in red. Little Ice Age, colder, drier, windier generally. And even before the medieval warm period, probably warmer, probably more windy in periods, less windy in periods than now, and certainly drier. But what this looks like a busy graph, but really this is every paleo-proxy record we have for temperature and moisture in Central Asia from those 6 countries. And what they really don't show us is any sort of an annual signal. When during the year it's warm, when during the year this moisture comes. And so that's what we're hoping to get out of our new record, is really, what does an individual year look like? When is moisture delivered? Will we be able, how has that water tower filled up throughout the year over time, and whether or not that seasonality that we see now has held. So we process our core. We really have 2 kinds of data, 2 kinds of records that I'll be presenting here very quickly. We have one continuous melter record that's about 1 centimeter resolution. That goes the full length of the core. I'll show you lead from that record in a minute. We also have our Keck laser facility ultra high resolution laser ablation system, where we get 500 samples per centimeter. I'm going to show you some data from that machine, where I can show you 1,600 years ago, we still can show you individual dust peaks for each year. So first of all, of course, I said 2,000-year record. We have 4 identified volcanic events in the core. We have 2 carbon-14 dates. Everything lines up with the flow model that comes from our understanding of accumulation on this glacier. Once we put together our initial time age depth curve for this, we can calculate what the annual layer thicknesses should be throughout the core. That's this blue curve here. When we observe with the ultra-high resolution data, what we find is that it matches almost exactly. Those red dots are what we observe in the core. We have a robust age depth scale for this record. So what does that look like? Going back 2,000 years is this blue record. This is lead, just lead. These other 6 curves are also Northern Hemisphere lead records from the last 2,000 years. Green is the Colnafetti core, and brown is the Mount Logan core of similar length to what we have. Both records have been worked on by people from Climate Change Institute. Other Asian cores, Central Asia, this orange core Inalchek goes back through the 20th century. Garangi goes back to maybe the bottom of the Little Ice Age, but certainly not into the medieval warm period or before that. So we've extended back to, on the scale of some of these longer cores in other parts of the Northern Hemisphere, our ability to characterize climate change over the last 2,000 years. I'm going to, in the next slide, focus in on these 2 sections of just the Europe and our Central Asian part of the lead record during the 20th century here and during the 1300s. Here in the 1960s and 1970s, when we started to understand really what lead was doing to people, and lead abatement technologies and policies were put in place in Europe, we see an immediate decrease in lead in ice core records that doesn't exist in the Central Asian records. I'm going to stop short of saying why that is, even though these 2 areas are connected by the Westerlies, but it's significant. Maybe more interestingly, here in the 1350s, this is work that was done by the Ice Core Research Group here, working with collaborators at Harvard and other institutions. They noticed a massive decrease in lead in their record in the 1340s to 1360s that exactly coincided with an epidemic of the Black Death in Europe. And in our core, we find the exact same shape. Even the decrease, a slight increase, a decrease again before coming back up to Black Death amounts. So several things here. We think probably we're seeing that Black Death signal is moving from Europe into Central Asia. Certainly, this may function as a nice dating stratum for ice cores in this part of the world. And also, if we back up actually just one, what we see here is that we get during that decrease in lead during the Black Death, it actually gets lower. Lead in our core and in the European core is lower than it is at any point in the 2,000 years before that. Suggests that we have less, that humans have been affecting the amount of lead in the environment for at least that long. So we'll move on to the seasonal records. This is a look at 3 dust species, or three dust species in our core at 1,600 years ago. Green is magnesium, blue is calcium, essentially measures of continental dust into the record, and red for the next 3 figures also is iron. You can see here gray and white is alternating year bands to show you, even at 1,600 years ago, we can see annual peaks in all 3 of those dust species. And I say iron is an indicator of northerly incursion into Central Asia. This is where the iron is in Central Asia. This is our ice core. Most of the air, again, remember, wind comes across the Caspian Sea region. This is where we have large outcrops of iron-containing sands, large banded iron deposits, and huge numbers of iron mines. So anytime we see iron in the core, we can assume that means wind is coming in from the north. Pre-medieval warm period, remember, so this is warm and generally dry. We have peaks in all of our dust species simultaneously with big hiatuses between them. Every year we have a big incursion during one stable season of iron-containing dust. During the medieval warm period, the dust goes down and we still have an annual stable peak in iron. And as we move forward into the Little Ice Age, where we have lots more dust coming into the record, coming into the ice core, that annual peak in iron breaks down, suggesting that we're having a much less stable annual signal, less stable annual seasonality, and we're getting northerly incursions throughout the year. I have been clammed up, so I'll take any questions.
right is the Black Death. What's the dip on the left?
This here or this?
That one.
There were quite a number of Black Death
More.
epidemics,
Okay.
so probably more Black Death.
That's what I wondered.
I don't want to plague you with Black Death questions, but I have to ask, is there any chance of recovering pathogens in the ice?
Doubtful.
I mean, you're
But-
pretty far. Are there ice cores closer to the actual area of infection?
Is anybody here who works on the Colmafetti core? No.
No, they're quarantined.
Yeah.
Oh!
I doubt it. I don't know how big a pathogen is, but mostly, I think these are mostly soluble. This can be largely soluble or very small dust particles that are making it. So.
Okay. Thank you.
It's relevant to point out that curve is a logarithmic scale.
Yes.
If you go to the one that shows the full length of the core, it's an incredible decrease.
Yeah, it's several orders of magnitude decrease in the amount of lead that was delivered. Yeah, I should say these are all logarithmic scale, and for all of the other, for the dust here, these are also logarithmic scale. And so you see between something like the medieval warm period and the Little Ice Age, it's orders of magnitude differences in the amount of dust that's being delivered in terms of just the general continental dust, whereas the total amount of iron that comes in is about the same throughout the whole record. See, that's on the same scale. So about the same amount of total northerly air incursion happens, but just on different seasonal scales.
Next, we have Mario Williams, who'll be talking about a Holocene record from Jamaica.
Hi everyone. My talk today is about prehistoric human, environmental, and climate changes in Jamaica. And Jamaica is an island that is located in the Caribbean biodiversity hotspot, and it is known for its very rich plant and animal communities. Jamaica was first settled based on radiocarbon archaeological dates approximately 650 AD by the Osteanoid culture, and they were replaced approximately 300 years later in 900 AD by the Malacan culture. And the Taino culture developed on the island in approximately 1200 AD. And next we had Spanish settlers led by Christopher Columbus landing on the island in 1494, and they were replaced by English colonizers in 1655. Then we see the establishment of the sugar plantation economy on the island, which reached its peak between 1700 and 1850. And in more recent times, we see the rise of areas of dense human settlement and urban centers such as Kingston and Montego Bay. Within the broader context of human migration within the Caribbean and the Greater Antilles being those four large islands in the center of the Caribbean Sea, Cuba, Hispaniola, Puerto Rico, and Jamaica, the date of first human arrival appears anomalous. Based on radiocarbon archaeological dating, Cuba was settled in approximately 5,100 years before present, Hispaniola approximately 5,500 years before present, and Puerto Rico based on a series of dates between approximately 4,800 to 4,000 years before present. And Jamaica was settled in 1,300 years before present, which begs the question, why is it that these large nearby islands were settled at such an early date in comparison to Jamaica? And over the course of the Holocene, we know that Jamaican ecosystems have been threatened by human activities in a variety of ways. In prehistoric times, we know that these cultures were using fire to manage their landscapes, whether by horticulture or by small-scale garden agriculture. And we also know that they were harvesting both marine and terrestrial organisms at rates that would impact those biological populations. And in the historical period coinciding with colonialism in the region, we see the removal of native vegetation and land clearance becoming an issue, and also the introduction of exotic species, including both competitors like old world rats, and also predators such as Herpestes auropunctus, which is the mongoose pictured on the slide. And in more modern times, we have urban sprawl threatening ecosystems, and also bauxite mining, where large swaths of land are cleared, and then bauxite is removed and exported to resource-rich countries, such as those in Scandinavia and Canada, in order to be processed and then to make aluminum. Based on this background, I developed a few guiding questions for my research project. And these include, how has Jamaican vegetation responded to natural and human disturbances over the course of the Holocene? And the earlier question which I raised, which is, when did humans first arrive on the island? To address these questions, I used a paleoecological approach, where I collected a lake sediment core from Wash Pond, and I chose Wash Pond as my study site for a number of key reasons. It's the largest freshwater lake in Jamaica, and it's also very close to the Black River Lower Morass wetland, which is an internationally protected wetland under the Ramsar Convention. And it is also close to known prehistoric osteoid and taino archaeological sites. I assessed 4 major proxies in my paleoecological analysis, and these include pollen grains, which is an indicator of changes in vegetation composition, diversity, and structure over time. Charcoal, which is a marker of fire regimes, which is the intensity or frequency of fire through time. A suite of dung fungal spores, which indicates herbivore abundances through time, which might inform us about changes in grazing intensity, and also stable oxygen and carbon isotopes from ostracod shells. And this is an indirect proxy for relative aridity in the region. And here we have our charcoal record that was developed. And on the y-axis, you have char, which is charcoal accumulation rates, and that's represented by the gray curve. And on the x-axis, we have time. And the black solid horizontal line at the base of the graph is background charcoal levels. So whenever the gray curve rises above the black solid line, we have increases in fire activity. And when the osteoid arrived on the island in 650 AD, indicated by 1 on the graph, we see our first initial increase in fire activity. When the Malak had arrived in 900 AD, indicated by 2, we see a sharp rise in fire activity above background levels. And number 3 and 4 on the figure coincides with arrival of the Taino on the island in 1200 AD and Spanish colonists in 1494. And we see 2 small, relatively smaller peaks in fire activity above background levels. Here we have our prehistoric fire curve once more, but superimposed over that curve is a number of important ecological and climatological trends, which is important for understanding the story. And based on our pollen analysis, the green tile, we identified a swamp mangrove fern forest at the base of our record. And this forest was replaced by a suite of disturbance taxa, including species from the families Amaranthaceae and Asteraceae. And these are associated with land clearance and farming and disturbance on the landscape. And this period with disturbance taxa, the yellow tile, also coincided with that blue arrow, which is a more wet climatic period. And it also coincided with the largest increase in fire activity that we saw in our record. But important to note from this diagram is that that black horizontal line indicates that that swamp mangrove fern forest failed to reestablish for the entirety of the record after it was lost, after that period of disturbance, and after the arrival of the osteoid, which is shown by 1 on the figure. We also identified a number of major northern hemisphere climatic events in our paleoecological record, and this includes the Little Ice Age, which is a period of abrupt climate cooling between the years 1400 and 1800. And based on several paleoecological records that were previously collected in the Caribbean region, we know that the Little Ice Age was arid. And in our record, so here I have the stable oxygen isotope record and stable carbon isotope record. Important to note is that positive values indicate periods of aridity and more negative values indicate more mesic climates. And the red tiles indicate aridity and blue tiles indicate wetter climates. And we see that the temporal span of the Little Ice Age indicated by the black arrows also coincides with increased aridity. Therefore, it was dry in Jamaica during that period. So therefore, 4 waves of human colonization on the island, the osteoid, Malak, and Taino, and European colonists, coincided with large vegetation shifts and also increases in fire activity above background levels. And we also saw that a very vulnerable ecosystem, the swamp mangrove wetland, failed to reorganize after a period of increased disturbance and fire activity, which also coincided with the arrival of the osteoid on the island, which might provide very important information for conservation managers who are tasked with protecting these important wetlands located on the coast of Jamaica. And we also found that a little ice age was arid in Jamaica, which suggests that this climate event was regionally coherent within the Circum-Caribbean basin. This brings us back to our first question. When did humans arrive in Jamaica? And some scholars suggest that rough marine conditions surrounding the island deterred earlier archaic peoples from traveling to Jamaica, until the Osteanoid developed novel maritime and navigational technologies such as larger canoes, which allowed them to traverse the void and land in Jamaica. However, another school of thought might suggest that resource utilization patterns by these earlier cultures did not involve the use of fire at levels which is detectable by our methodology. Or perhaps climatic and environmental conditions were not favorable to the ignition and proliferation of large fires. And with that, I'd like to thank many individuals who were extremely helpful with the completion of this project, including my advisor, Dr. Jacqueline Gill, Andrea Nurse, Matthew Goldsmith, Abigail Poirier, Zach LePage, and the entire Beast Lab. I'd also like to thank individuals in the community at the University of the West Indies, which is located in Kingston, Jamaica, who are extremely helpful with collecting my core and with many technical and logistical details associated with this research. Also, the Jamaican government, many agencies there who helped me to secure permits. And for financial support, the Dynamic Churchill Exploration Fund, the National Aulacoseira Core Facility through their Visiting Graduate Student Grant Program, and also 195 donors on experiment.com, which helped me to raise funds for this research project. And I'll take questions. Thank you.
Which of the explanations do you favor?
For which of the changes?
For the humans not getting there, you.
Yes, so I think that humans would have most certainly been able to make that trip. I think that during that period of time, we see where a canoe that was imaged can hold 50 to 60 individuals. And I think that these prehistoric cultures, perhaps we don't give them enough credit for their navigational abilities. I certainly think that they'll be able to make it there. So I believe it has more to do with detection of fire and clearly capturing that signal. And it might have to do with the use of proxy. So here I show the macro charcoal record, which is more of a local fire signal. And perhaps the micro charcoal record might add some nuance to that story. And people also use a variety of different chemical bioorganic markers. So levoglucosan, menosan, and polycyclic aromatic hydrocarbons, which can tell you about the source of fire. So whether it was grasslands or forest burns or burning, or maybe materials associated with a human settlement, which might add some additional information to that. But I can definitely say that I still, even though the mystery remains, I still believe that people were there earlier than the Osteanoid culture.
Just to follow up on that, for the other three big islands, which are earlier dates, those dates have always struck me as very suspiciously close to sea level stabilization. People arrived by they see they had to. If they're maritime adapted, they may be living along the coasts and having a lifestyle that would not leave the signals you're talking about. So you may well be right for Jamaica as well. But that's something to think about, how you might find coastal settlements that are maritime oriented only before they start doing inland agriculture and affecting the landscape in a broader way.
Yeah, thank you.
And I'd like to talk to you about that.
There's a cross-island comparison to be done as well, because there's a similar paleoecological record being developed on the southeastern part of the island currently, where they'll be looking on pollen and fire. So it'd be interesting to see if there's variation across the island in thinking about a local signal versus a regional signal from the fire proxies.
Excellent. Thank you.
Okay, thank you.
Okay, next up we have Bonnie Newsom. This is going to be talking about ceramic tempers in Maine.
Hello, everyone. Thank you for coming. Today I'm going to be talking about some recent findings on archaeological ceramic tempers from the Holmes Point West site in Maine. Let me get my clicker here. Aboriginal ceramics in the Northeast provide archaeologists with some unique opportunities to explore choices of indigenous potters. And these choices are influenced by the cultural, historical, and environmental context within which they're made. Let me just back up. This is an example of ceramics from the Penobscot River Valley, and the woman on the right is making a coil-based type of pot. We think this is similar to what folks here in Maine were making. Ceramic tempers can be especially informative in terms of understanding geology, environment, human mobility. Temper is the aplastic material added to clays that they improve pot performance, clay workability, and they aid in the pottery firing and cooking process. So potters throughout the world use different types of materials as temper, including grog, which is crushed up ceramics, shell, fur, hair, bone, minerals, rocks and minerals, as well as plant-based materials. And each of these materials has technological advantages and disadvantages, and their use is influenced by potters' histories, their skill, as well as cultural protocols which may surround pottery manufacture. But despite kind of the variety and temper options available to past potters, archaeologists in Maine have rarely considered the use of temper types beyond kind of crushed rock and shell. Temper classifications are often restricted to identifying what the minerals are in temper, or they are classified very broadly as shell or organic. And here are a couple examples of temper. The one on the right is crushed rock, the one on, other way around. The one on the right is shell, and the one on the left is crushed grit and rock. The term organic is a catch-all term used to describe some of the aplastic materials that have leached out of the clay matrix. And you can see here, there's some voids in the paste that are left by shell that has eroded out. Recent analyses of Aboriginal ceramics from the Holmes Point West site in Machias, Maine suggest that potters may have used plant-based materials in the ceramic manufacturing process. Imprints and ceramic sherds from the site are reminiscent of conifer needles. And this suggests a broader suite of tempering materials than what's been recorded from Maine previously. And I'm just going to talk about these briefly. The Holmes Point West site is located in eastern Maine in Machias Bay. It's part of a cultural landscape which includes multiple archaeological sites in the area, most of which date to the ceramic period, which is roughly 3050 to 250 BP. It's a multi-component site and it's produced evidence of both pre-contact and post-contact occupations. And Aboriginal ceramics from the Holmes Point West site are attributed to primarily the Middle Ceramic period. There are some late ceramics from there as well. And that's roughly 2150 to 450 BP. Formal archaeological research at the site was initiated in 1973, and then again in 2008 through 2014. These later excavations were conducted under the direction of Dr. Brian Robinson. So the discovery of conifer needle imprints in archaeological ceramics from Holmes Point West happened by chance. In 2017, we initiated some preliminary analysis of the ceramics in preparation for continued field research at the site. And during this analysis, Matthew James, who's the work study student, noted these elongated imprints. Right here, as you can see. And you'll note that they are within the vessel walls. And he noted these in multiple sherds. It wasn't just by chance we had one sherd, but he noted them in multiple sherds. So given the occurrence of shell-tempered pottery in ceramics from Maine and the Maritimes, imprints in voids are not uncommon in ceramics. However, the imprints identified by Matt actually did not exhibit the same characteristics that we see in pots that have been tempered with shell. In fact, they happen to be quite uniform in size and morphology. And we discovered that pots with these imprints were assigned to multiple temporal units, so they spanned a long period of time. So we compared our imprints with local floral imagery and needles and determined that the imprints were reminiscent of conifer needles. And then we decided to go to the experts, and we talked with Aram Calhoun and Andrea Nurse, who provided us with some tentative identifications of balsam fir. And many of the impressions are incomplete due to breaks in the ceramics. And the possibility does exist that other conifer needles, such as hemlock, spruce, and pine, are represented in the assemblage. But based on our observations and our consultations with Aram and Andrea, we're confident that the voids in the ceramic paste are, some of them are balsam fir, and however, we do acknowledge the need for additional study for further confirmation. You can see these are examples of, these are examples of balsam fir needles, and you can see this is one of the imprints in the pots. 16 vessels from Holmes Point West actually have these types of impressions. 13 sherds that were not able to be assigned to a specific pot also has them. And then we have one manufacturing scrap. Manufacturing scrap is part of the ceramic production process where for some reason people take little scraps and we'll find them later and they've obviously been fired, but we have one of those with evidence of these imprints. This image here shows an intact, what appears to be an intact needle, ceramic, conifer needle. And if you look up close, you can see these little white dots. And this, I don't know if this is something that we can determine are actually the stomata that exist on the balsam fir needle. So I'm happy to hear from anybody who has more expertise in this than I do. So we do also have some references to plant-based or vegetal temper in Maine. In 2007, Will and Moore noted some grass-like imprints in ceramics from Millinocket Lake. In 1884, actually, an archaeologist by the name of Matthew noted a conifer needle imprint in ceramics at Boquebec, New Brunswick. And I recently talked to Michael Deal out of Memorial University, and he had mentioned that he recalls seeing a conifer needle in ceramics from Nova Scotia, although he couldn't tell me at the time, where exactly in Nova Scotia it was. So these findings prompted us to consider whether potters were incorporating these needles intentionally or if they were accidental inclusions in the clay. And we actually think they were intentional. We're seeing them in the manufacturing scraps. We see them in multiple vessels spanning roughly 1,700 years, indicating long-term behavioral practice. And by and large, potters aren't careless. Having impurities in your clay will affect your firing ability, your drying, your cooking performance. So I think potters are probably adding them intentionally. So if they are adding them intentionally, why? And these are my reasons. I'm getting the clam up sign. So voids in the ceramics or inclusions inhibit micro cracking, which is occurs during cooking. Vegetal tempers make lighter pots. Water absorption, it aids in the manufacture and reducing the stickiness of clay. And it could be some sort of medicinal addition to the pot, or, balsam fir smells great. And so with that, I will pass by these and just acknowledge folks funding Maine Academic Prominence Initiative and Humane Work Study Program, our experts, Aram Calhoun, Andrea Nurse, and Andrew Heller did some amazing things with the pottery, and always the indigenous peoples of Maine for letting us research their archaeological heritage. Thank you.
Have you considered doing an ethnoarchaeological project and trying to make balsam needle pottery?
I think that's on the agenda, yes. I think I could do that fairly easily, yes.
Could I ask to see the ecological implications?
Oh, sure. Balsam fir is present in eastern Maine between 2150 and actually that should be 450 BP, provided that pots were brought to the site or weren't brought to the site from elsewhere. So you always got to be a little cautious when people are involved. And it supports paleo environmental reconstructions for eastern Maine, mainly Schaffler and Jacobson, 2002. Serves as a well-defined temporal reference for past ecologies. We have some good resolution on our ceramic designs, and we know how they change through time, and we can narrow these things down pretty well. It encourages a broader analytical approach to archaeological ceramics that has not been conducted in the past, and we get new inquiries about human behavior. So,
I have a million questions, but my simplest one, which I'll ask publicly, is in the pots that you're finding these impressions, is there other temper?
yes, there is. It's usually, it appears to be crushed granite.
So it's grit and.
Yes, it's a combination for the most part. I think
I'll
we
ask
have.
you other ones later.
Okay. Anything else? Well, thanks so much.
All right, so last up, we have Danielle Levesque, and she's going to be talking about house squirrels.
Great. I thought I should say that I have a 2-minute talk, so I'm not just rushing through a 15-minute talk in 2 minutes. So I thought I'd give a bit of an update on Vanessa Hensley's master's project. So Vanessa has unfortunately moved on to bigger and better things and defended her thesis in January, but I thought it would be great to show off some of the amazing research she did during her 2.5 years at the University of Maine. So we have a bit of a story here going on with some of the small mammals in the state. We have 2 species of flying squirrels, and their sort of historical current distributions are shown here. But what we know is the southern ones are slowly moving up. And so a lot of people say it's because winter temperatures are getting warmer, so the southern ones are able to move up, and they're pretty good at outcompeting the northerns. But we were really curious about whether or not their responses to heat are playing a role in this too, because these are species that nest in trees during the day, so they're active at night, and in the daytime they're stuck sleeping in these tree hollows that they have absolutely no control over the microclimate of. And there's very few tree hollows in the forest, so they're limited by their habitat. So the way we go about looking at these things is we stick them in little boxes and we look at their responses to different ambient temperatures in terms of how much water and how much energy they use at those high temperatures. I won't show the results for that, but what I will show is the other thing we do where we implant these temperature-sensitive data loggers, like this little one here, into the flying squirrels. This is just their feet when they're knocked out. They're really gorgeous. This is the northern flying squirrel. It looks like they have little snowshoes. They're fantastic. Stick radio collars on them, let them run about the forest for a couple of months, and then get the data back. And so just to show you a trace from one individual, here's ambient temperature, and the gray bars are nighttime, and body temperature is in black here, and so you can see they are active at night, but what you also can see is during the day, their body temperatures are dependent on the tree holes they're sleeping in. And so at the moment, we have one part of the picture. These are all data from southern flying squirrels. So what we basically have is responses to heat in southern species at the northern edge of its range. And so I have a new master's student who's going to be joining us from Maine, Presque Isle, who's going to be working on the northern flying squirrels up in Presque Isle because we finally found them. They're still in the state. And so it's kind of a watch this space. And so the last thing I wanted to say that we found that's kind of cool is flying squirrels run really, really hot. So here's their body temperature when they're active, and compared to, this is body temperatures for all mammals, active squirrels and resting squirrels are on the high end of things. So another thing I'm interested for my research is why are squirrels so hot, and what does it mean? So it's more of a watch the space with time, but I thought I'd give you a quick introduction today, and now I'll go ahead.
Do they get Lyme disease?
So I don't think they're part of the equation. Doesn't, Susan, do you know? Do people look at them?
Yeah, I mean, they close to your test.
Okay, but we don't know if they're good reservoirs.
I don't
or
think
not.
they're reservoir.
Okay, yeah. So we are also looking at the white-footed mouse and the deer mouse because the same story is happening where the white-footed mouse is moving up, and they're the ones that are really good with Lyme disease.
Yeah.
So I have students looking at the heat responses to both of those two. How much that is.
Interesting.
Yeah. Well, flying squirrels are a bit harder to catch, and they're not found in a lot of disturbed forests. Canvas is great for them for some reason, but they're a bit harder to find than gems. Well, thank you.
I just wanted to say hello.
Okay, just before we take off, I realized I should have done this when we started, because some of you haven't been here before, and you're hearing references to clam up. I just want to make sure you know what that is. This is probably my most enduring contribution to the Climate Change Institute. I also want to thank everybody who came and presented today. They were great presentations. Before we started, one of the students unnamed told me that he or she almost didn't make it and was, I quote, really glad not to be a hole in the program. And I'm glad that none of our students are holes. We should thank them all. We will now move on to the cash bar and the posters. So when you get a drink, be sure to go look at the posters and talk with the authors of the posters. We will have dinner at 5 and our keynote speech at 6.
Well.